Okay, so we have done the intuition behind backpropagation. Now we want to take this intuition forward and get into the mathematical details of how backpropagation, or how do you compute these partial derivatives or gradients that you are interested in, right? So this was the outline. So we said that we are going to slowly talk to all stakeholders in the neural network, and we had divided this into three parts: talk to the output layer, talk to the hidden layers, and talk to the weights. So I'll start with the first part, which is talk to the output layer, right? So that's what we're going to do now, right? So let's see, what do you mean by talk to the output layer? I'm interested in computing the derivative of the loss function with respect to the output layer, right? So this is the output layer, right? I collectively call it as the output layer, although it has two parts, activation and pre-activation. I'm going to call this layer, which is the A's, is what I'm going to call the output layer, right? So I'm interested in the derivative of the output layer of the loss function with respect to this output activations or output pre-activations. Okay, so that's the quest that I have, and this I know would be a collection of some partial derivatives, right? So partial derivative of the loss function with respect to the first output neuron, with respect to the second output neuron, and so on, right? And this would be the loss function here, similarly the loss function here, right? So this is the quantity, this entire vector, which is the gradient vector of the loss function with respect to the output layer, is what I am interested in. Okay, now to begin with, right? So, and I know what the loss function is. I know that this is minus log of y hat L, where L is the true class label. Okay, and what I'm going to do is I'm going to focus first on the upper half, right, which is the green, dark shaded green portion, right? So what do I have here? I have y1 hat, y2 hat, all the way up to yk hat, okay? And my loss function is minus log y hat L. That means one of these, my negative of the log of one of these values. Which value? The one which corresponds to the true class label, right? So that's what the situation is. So that's what my loss function is, and I'm trying to take its derivative with respect to one of the values. It could be y1, y2, all the way up to yk, right? So now this is what I am trying to do. I'm trying to take the derivative of the loss function, which has the term y hat L, with respect to one of the yi's, okay? And we know that this log y hat L depends only on one of the elements in this array, the one which corresponds to the true loss function, right? So in particular, let's take an example. Suppose L is equal to 2, that means the second class was the correct class. Then the loss function would in effect be minus log hat y2, and now I have trying to take the derivatives of this with respect to any one of these, right? Because I have considered a generic I here, right? So this is an I, so any one of those elements. So if I am trying to compute with respect to y1 hat, of course the loss would be 0, right? Because this quantity does not depend on y1 hat. There is no y1 hat that shows up here. If I try to compute with y2 hat, then it would be minus 1 over y2 hat, because that's the derivative of, so if you want to compute the derivative of log x with respect to x, that's 1 over x. So the same thing apply here. Instead of x, we have y2 hat. If I want to compute with any of the other guys, y3 hat, y4 hat, up to yk hat, it's going to be 0, right? So that's very straightforward. So what does it mean? It's like an if-else condition, right? So this is going to be equal to minus 1 over y hat L if I and L tend to be are the same. That means the quantity that I am taking the derivative with is also the quantity that is there inside the log. Then it would be minus 1 over y hat L. Otherwise it would be 0, because then I am taking the derivative of one variable with respect to another, and they don't depend on each other, right? So this is very straightforward. I have computed the derivative of the loss function with one of the entries here, any generic entry here, and it would either be 0 or 1, right? So how do I write this formally? Does anyone know that? Yeah. So some of you might have heard of this indicator variable, right? So what does an indicator variable mean? So let me just explain. So I'm going to write the derivative of L theta with respect to yi, and again I repeat, I can go from 1 to up to k, right? Is equal to the indicator variable. So this one here is the indicator variable. I should have written it as this kind of a 1. Okay. And what's the condition associated with that? I have suffixed something there. So this is what it looks like, right? I equal to L. So what that means is that if I is equal to L, then this indicator will take on the value 1. Otherwise, it will take on the value 0, right? So that's what an indicator value variable means. It just encodes this if-else condition, right? So indicator variable this is how you write it, and it will take on the value 1 if the condition is satisfied, that the condition in the suffix is satisfied, otherwise not, right? So you can now agree that these two are the same, right? This is just a more compact way of writing that, right? Okay. So what do I have so far? I have the derivative, the partial derivative of of the ith shaded green guy, the partial derivative of the loss function with respect to the ith shaded green guy, right? But we are not interested in one partial derivative, we are interested in the entire collection of partial derivatives. So I want to talk about the gradient with respect to the vector y hat, not just the partial derivative with respect to one of the elements of this gradient, right? So what do I mean by that? So this is I'm going to write the gradient of the loss function with respect to y hat, right? So this is what my notation is. And what does this mean, right? This is what it means. It's just a collection of the partial derivatives of the loss function with respect to all the elements of y hat. And what are all the elements of y hat? y1 hat, y2 hat, all the way up to yk hat, right? So it's just a collection of all these guys. And I have the formula for any one of them, right? So this is what the formula looks like. The formula was indicator variable L equal to I divided by y hat L and the minus of that, right? So if I want to compute the derivative of the loss function with respect to y1 hat, in that case I is equal to 1. So hence I will write I equal to 1 here. And L of course remains the same, right? L does not change. So that 1 by y hat L and the negative of that comes outside, and this indicator variable just changes as I go down the vector. The condition associated with the indicator variable changes, right? And since only one of the, L could take on any one of the k values, this vector will have 1 in only one position and 0 everywhere else, right? For example, on the previous slide we were discussing that suppose L equal to 2, that means the correct class is the second class. Then when I evaluate this indicator variable, which is L equal to 1, I will get the answer as 0. For the next one I will get the answer as 1, and everywhere else I will get a 0, right? Similarly, if L is equal to 3, then I will get 0, 0, 1 and then all 0, right? So only one of these elements would be 1. So these kind of vectors are called one hot vector because only one of their entries is going to be 1, right? So let me just clear the slide. Okay. So this is what it looks like. I am going to call this vector as the one hot vector EL, where this contains a 1 in the lth position. This is a vector containing 1 in the lth position and 0 everywhere else, right? And that's just a more compact way of writing this. I have not done anything new. I have just introduced a new notation for the vector E, right? Okay. So far so good, right? So what have we been able to do so far? Remember that this was H3, this part was H3, which was the same as y hat. Sorry, I should have written H3 in the suffix, right? So I have the derivative of the loss function with respect to y hat. But that is not the quantity that I was interested in. I was interested in the derivative of the loss function with respect to A3, right? Or AL, because L equal to 3 in this case, right? So that I have not done yet. But what I have done, the reason I did this part was to give you the, like with the help of a smaller example, right? Try to explain how this entire discussion is going to go. What did we do? We first computed the partial derivative with respect to one of the elements. So we were actually interested in the gradient with respect to the entire vector, but we didn't go there directly. We first computed the partial derivative with respect to one of the elements, and then once we had that, we were able to write down the formula for the entire vector, right? So this same recipe is going to repeat everywhere. We are going to first try to, whenever you're interested in a derivative of some quantity with respect to a vector, we'll first try to find out the partial derivative with respect to one element of that vector, right? And then generalize for the entire vector. Okay, that's what we are going to do. So now with that, let me just try to find the derivative of the loss function with respect to AL, and what I am going to do is first try to find the derivative with respect to one of the elements, which is the ith element. So again, AL is actually AL1, AL2 all the way up to ALk, right. So from with respect to any generic element of that vector, I am trying to find the derivative of the loss function. What is the loss function? Minus log y hat L. So now what is this going to be? I can split it into two parts. I can write it as the derivative of the loss function with respect to y hat L, and then the derivative of y hat L with respect to ALI, right. They can split it into these two parts, okay. And now the question is, does y hat L depend on ALI, right. So what am I asking? This is what I am trying to ask, right. So this is what my A vector looks like, okay. And my I here in this is anything from 1 to k, right. And let's again consider the case when the correct output was 2, right. So that means my loss function is minus log y hat 2, okay. And that's why this I am trying to compute the derivative of y hat 2 with respect to some ith element, right. It could be AL1, AL2, AL3, anything, right. So now I'm asking, does y hat 2 depend on all these A's, or does it only depend on one of them, right. Because earlier we saw that the loss function depended on only on one of the y hats and not the entire vector. For all the other elements, the derivative was 0. But now for y hat 2, which is this green guy, not the loss function, right, this shaded green guy, does it depend on everything, every element of A? It does, right, because how did you compute y hat? Y hat was computed using the softmax function. So y hat 2 in particular was e raised to AL2 divided by the summation of e raised to all AIs, right. So it depends on all the AIs because all the ALIs appear in the denominator, right. So it's a function of all the LIs, right. This is how we had computed it, right. So this should be clear that now we are trying to take the derivative of y hat L with respect to ALI, and hence it's a function of all the variables. Okay, so now that we have understood this and we understood what the formula for y hat L is, let's try to find this, right? Let's try to derive this. Okay. Okay. So this is what we are trying to do, right? We are trying to compute the derivative of the loss function with respect to one of the elements in the AL vector. Okay. Now this is going to be, and I have already established that y hat L depends on all the A's, right. So it's not going to be the case of 1 in some cases and 0 in other cases, right. That the derivative is 0 in some cases and not 0 only in some cases. The derivative would always exist. Now this is a derivative of the form derivative of the form of log of a quantity with respect to a variable, and that quantity depends on that variable. So this would just be 1 by y hat L, 1 by y hat L, and then the derivative of y hat L with respect to ALI, right. So this is just the chain rule applied, right. So this, if you have derivative of log of x square with respect to x, right, then you will first write it as 1 by x square and the derivative of x square with respect to x, right. The same thing is happening here. Here now, instead of x and x square, which is very straightforward, I have ALI and I have y hat, and just as x square is a function of x, y hat is a function of ALI. So the same thing applies here. I'll first take the derivative of log of y hat with respect to ALI, which would be just minus 1 by y hat Li, and then the derivative moves inside, just as what has happened here, right. This high school calculus, I'm sure you know this, but I just did it in some detail. Okay. Now let me just replace y hat L by what exactly is y hat L, right. So let me explain what this formula means, right. So what was y hat is actually the softmax of AL. What does that mean? That AL was a vector, right, which had these components AL1, AL2 all the way up to ALk, and then how did I compute y hat from that? y hat was computed by applying the softmax function, which was e raised to al1 divided by the summation e raised to al2 divided by the summation, and so on, right? So this y hat is a vector, al is a vector. So this softmax of al is actually a vector, and what this is saying is that I am looking at the lth element of that vector, which is the same as y hat l, right? So that's what this formula is saying. Nothing great here. And what is the lth element of y hat l? It's going to be e raised to al, again suffixed with l, divided by the summation of all the exponents, right? So that's what y hat l means. That's what softmax of, this is softmax of the vector al, and then taking the small lth component of that, right? So that's what that notation means. Okay, let's go ahead. So I'm just going to, as I said, what I just explained, that y hat l, which is the same as softmax all, is essentially this guy, right? So I've just put in the formula for that. Sorry, this should have been I, right? Because here the index is over I. So I'm summing over all the exponents, okay? Now, this is a derivative of the form u by v, or I can call it as derivative of the form gx by hx, right? And we all know the formula for that. This is the formula for the derivative of u by v, right? And you would have again known this formula. I will not go into the details of that. You can refer to it. If you don't know this, just maybe quickly brush up some calculus and you will realize that this is the formula, okay? Okay, so let's go ahead. Now, so I'm just going to substitute this formula blindly, right? So this is g of x for me, and this is h of x for me. So I'm just going to substitute g of x and h of x. So this is derivative of g of x with respect to x. So I'll have derivative of, this is my g of x with respect to ali into 1 by hx. So I'm just dividing it by h of x, right? And then I'll not explain this entire formula, it's like too cumbersome to speak it out, right? It's not difficult, but it's just too cumbersome to speak it out. This is again g of x, as you would notice. This is again h of x, so this is just what I'm substituting. Then this is h of x square, right? So all of this is pretty routine substitutions that I'm making in the original formula. Once you get that this is g and this is h, and you buy this formula, the rest of it is just plain substitution, right? Now let's start computing these derivatives. So now I am taking derivative of ali with respect to the exponent of all, right? So let's see what am I trying to do. Again, I had this vector al, which had components al1, al2, all the way raised to alk, right? Now I am considering this quantity, which is what? E raised to all, okay? There is no denominator here, right? It is just e raised to all. I am trying to take the derivative of that with respect to one of the guys here, right? And again, you can notice that this only depends on one of the elements here, where corresponding to the lth entry here, it does not depend on the other guys. So this would be 0 if I happens to be anything other than L, otherwise it would be 1, right? And we just saw how to deal with this on the previous slide. So I'm going to write it as this, that it's going to be e raised to x, right? You understand what I'm calling as e raised to x. So the derivative of e raised to x with respect to x is e raised to x itself. Here instead of x, we just have ali, right? So it's going to be e raised to x if L is equal to I, just as I explained here, sorry. Oops. Okay, so it's going to be if L is equal to I, then the derivative would be e raised to this quantity, otherwise it would be 0, hence the indicator variable. Then I have copied the denominator as it is from the other place, right? Now this quantity I have copied as it is here. The denominator I have split into two parts, right? So it's squares I have just put into two separate parts, and now I have this, right? So let's see what that quantity is. So here I have the sum of the exponents. So what does that mean? I have e raised to al1 plus e raised to al2 plus all the way e raised to alk, and I am taking the derivative of this sum with respect to one of the elis, right? And what will happen? All the elements in this sum will disappear except the one which corresponds to EALI. Hence, the derivative would just be e raised to ALI, right? So, this is again straightforward. I have a sum of terms, only one of them depends on the variable with respect to I'm computing the derivative. So, only that term will remain, everything else will disappear, right? So, all of this looks pretty straightforward. Don't worry if you're not getting it as I'm explaining it, you can just pause the video and look at it. It's very mechanical steps, right? So, it's this exp just looks very annoying, but it's just e raised to something, right? And you know the derivative of e raised to something with respect to that same variable is just e raised to x, right? So, that's the only formula that is being applied here, right? Okay. So, now let's get back. What is this? We just did that. Do you remember what that is? So, in the bottom I have the sum of all the exponents, right? So, again let me just do this. So, I had AL1, AL2 up to ALk. So, this the denominator is just the summation of the exponents of all these quantities, right? That's what this denominator is. And what is the numerator? The numerator is the exponent with respect to the ith guy. So, that means it's just the softmax. If you consider the softmax vector which I had said, which was y hat, then I am just looking at the ith entry of that vector. So, this is just y hat I, right? That's what it is. So, this is the ith entry of the softmax vector. Similarly, this is the lth entry of the softmax vector. Similarly, this is the lth, sorry, this should not have been L equal to I. So, this should have been lth entry, right? Not I dash. This should have been the lth entry of the vector. And now I can just write all this as this guy. I can just write it as y hat L. This guy I can write it as y hat L, and this guy I can write it as y hat I, right? And now, of course, the y hat L here and here gets cancelled, and so I'm just left with this, which is minus 1 L equal to I minus y hat I, right? So, this is what I have left with. Again, don't fret too much if you did not get it at one go. You just pause the video and you will get it. It's just a simple set of steps. So, this is where we are, right? So, we have the derivative of one of the loss function with respect to one of the elements of my output vector, right? And this is what it turns out to be. And now, I want to compute the derivative of the loss function with respect to my entire output vector. So, this is the quantity that I am interested in, and I know that is just a collection of these partial derivatives, right? So, it's the derivative with respect to AL1, AL2 all the way up to ALk, and I know the formula for each of these guys, right? Because this formula is for I, any generic I. So, I can substitute I equal to 1, 2, 3, so on, right? So, I can just substitute I as the appropriate value here, and this is what I will get, right? So, minus indicator variable L equal to 1, y minus y1 hat, y2 all the way up to yk. So, I have just substituted the I by the appropriate index and just expanded the vector, right? I have written down the full vector. Now, this here is just my y hat vector, and this here is just my 1 hot vector, in which only the lth entry would be 1 and everything else would be 0, just as we had done on the previous slide. So, this is just the difference between two vectors, okay, and the minus sign has been accommodated for appropriately, right. So, I think, yeah. Okay, this minus sign should have been outside, right, because this was there. Or, yeah, whichever way you could have thought of this as minus plus, minus plus, minus plus, and then you are left with this, right. So, these signs here are consistent with the signs that you had here, right. That's what is important, right. Okay. So, we are done with this. So, what have we done so far? We have done the derivative, we have done till this far, right. Remember, we were talking to every layer, and this was our first goal that talked to the output layer. So, we now know the derivative of the loss function with respect to the output layer. That means we know our first gradient, right, which is the gradient of the loss function with respect to output layer. This is a scalar quantity, this is a vector. So, what this tells you is that what happens if I change one value of each of the values of this AL vector, then what is the change in L theta, right? That is what each of these elements captures, and the collection of all those elements is just the gradient vector, the gradient of the loss function with respect to AL, right? So we are done with the first step that we had, which was to talk to the output layer. Now we are going to talk to the hidden layers, and then we are going to talk to the waves. Okay, so we'll come back and